Welcome to AP Precalculus, topic 1.13. In this video, we'll be exploring two essential concepts in mathematical modeling. First, we'll learn how to identify the appropriate function type to model a given scenario. This is known as function model selection. Second, we'll discuss the crucial role of assumptions and restrictions that underpin every mathematical model. This is assumption articulation. By the end of this video, you will be able to confidently choose the right tool or function to represent real-world data and understand the limitations of the model you've created. Let's get started. Let's begin with our first objective, identifying the appropriate function type for a given situation. By the end of this scene, you will be able to distinguish between linear, quadratic, and higher-degree polynomial functions by looking at the rates of change and graphical features of a scenario. The type of function we choose is determined by how the quantities in the problem are changing relative to each other. First, if you notice a roughly constant rate of change or a linear relationship, a linear function is your best choice. For example, if you save $10 a week, your savings grow at a constant rate. A graph of your savings over time would be a straight line. So, a constant rate of change indicates a linear function, which we write as f of x equals mx plus b. Second, if the rate of change is not constant but is roughly linear itself, or if the data appears symmetric with a single high point or low point, you're likely looking at a quadratic function. A classic example is the height of a ball thrown straight up in the air. Its velocity, or rate of change of height, changes constantly due to gravity. The path it traces is a parabola, symmetric around a single maximum height. This changing rate, symmetric curve, or single maximum/minimum suggests a quadratic function, f of x equals ax squared plus bx plus c. Third, we can look at the physical context. Area calculations often involve two dimensions, which typically leads to quadratic functions. Volume calculations, being three-dimensional, are often represented by cubic functions. Consider the area of a square. If the side length is s, the area is s squared. This is a quadratic function. If we talk about the volume of a cube, the volume is s cubed, a cubic function. To recap, we choose a linear model for constant change and a quadratic model for a changing linear rate of change, or symmetric data. We can also use contexts like area or volume to guide our choice. Now, let's explore more complex polynomials. Now let's expand our toolkit to include higher-degree polynomials. By the end of this scene, you will be able to connect the degree of a polynomial to the number of its roots, turning points, and the behavior of its differences table. Polynomial functions are used to model scenarios with more complex behavior. Specifically, if you see multiple real zeros or multiple maxima and minima, these turning points are a key visual clue. A polynomial of degree n can have at most n real zeros and at most n-1 turning points. So, if your data has, for example, 2 peaks and 1 valley, that's 3 turning points, which implies you need at least a degree 4 polynomial. There's also a powerful algebraic tool to help identify the degree of a polynomial, the differences table. The differences table is a method for finding the pattern of change in a sequence of values. Let's look at the sequence of cube numbers. 1, 8, 27, 64, and 125. Since this is a cubic function, we expect a constant difference at some level. Let's calculate the first differences. We subtract each number from the next. 8 minus 1 is 7, 27 minus 8 is 19, and so on. Now the second difference is 19 minus 7 is 12, 37 minus 19 is 18. This is the rate of change of the rate of change. Finally, the third difference is 18 minus 12 is 6, 24 minus 18 is 6. The third differences are constant and non-zero. This confirms our hypothesis. If the nth differences are roughly constant and non-zero, a polynomial of degree n is a good model for your data. In our example, the third differences are constant, so the polynomial has degree 3. Another key property is that any set of n plus 1 points with distinct inputs can be modeled by a polynomial of degree n or less. For example, you can always fit a unique line, a degree 1 polynomial, through any 2 points. You can always fit a unique parabola, a degree 2 polynomial, through any 3 non-collinear points. This is a very powerful concept for data fitting. Now, what happens if the behavior of our data changes abruptly? So far, we've talked about models that describe a continuous pattern, but what if the behavior of our data is different over different time periods or under different conditions? This is where piecewise functions become essential. A piecewise function models scenarios where the rules change for different intervals of the input. Think about a cell phone plan. You might pay a base fee for the first 10 gigabytes of data, but then a different higher rate for any data you use beyond that limit. This is a classic piecewise scenario. Let's formalize our quick model selection guide. This will be your go-to reference when you're faced with a new problem. First, if the rate of change is constant, your model is linear. Second, if the rate of change is changing and the data appears symmetric or has a single peak or valley, it's quadratic. Third, if you see multiple turning points, that is, multiple maxima and minima, you need a higher degree polynomial. Fourth, if the data shows different rules for different intervals, you should use a piecewise function. And finally, don't forget the powerful test of the differences table to confirm the degree of your polynomial. In this scene, we've learned how to identify the correct function type based on the characteristics of a scenario, from constant rates to multiple turning points to changing rules. Now, let's turn our attention to what every model leaves out: assumptions. Every mathematical model, no matter how complex, is a simplification of reality. It's a lens we use to understand a situation. And like any lens, it doesn't show the whole picture. This brings us to our second objective: learning how to describe the assumptions and restrictions that govern any model we create. Understanding these limitations is just as important as knowing how to create the model in the first place. The core principle is this: models are built on assumptions. These assumptions can be about constants, relationships, or the data itself. For example, in our ball thrown in the air model, we assume a constant force of gravity. This is a reasonable assumption over short distances on Earth, but it's an assumption nonetheless. We also assume the relationship between time and height followed a quadratic rule. Again, this is an assumption based on physics. A critical assumption we often make is that the data we have measured continues to follow the same pattern beyond our observations. This is extrapolation, and it can be dangerous if the underlying conditions change. Finally, we must always consider the context of the problem when defining the input and output values. These are called domain and range restrictions. A domain restriction might arise if we're modeling time. Time cannot be negative, so our model's domain would be restricted to time greater than or equal to 0. You might also have a restriction on a number of items which can only be non-negative integers. A range restriction might occur if our model outputs a value that must be a whole number, like the number of people. If our model predicts 7.3 people, we'd need to restrict the output to be an integer, perhaps by rounding. So, to recap, when you create a model, you are simplifying. You must articulate the assumptions you are making about constants and relationships, be cautious about extrapolating your data, and define realistic domain and range restrictions based on the real-world problem. Let's put everything we've learned together with a classic example from physics. Consider the trajectory of a projectile. Imagine a toy rocket launched straight up with an initial velocity of 49 meters per second. Our goal is to find the function that models the height of the rocket as a function of time, and to describe the assumptions we are making. Since the rocket's velocity changes at a constant rate due to gravity, and its path is a parabola, a single peak, we know this must be a quadratic function. We're modeling height as a function of time, so the variables are h and t. The general form for this model is h of t equals at squared plus vt plus s naught, where a is a constant, v is the initial velocity, and naught is the initial height. Now let's incorporate our given information. The initial velocity, v, is 49 meters per second. The initial height, s naught, is 0 meters since it's launched from the ground. The acceleration due to gravity on Earth, a, is approximately minus 4.9 meters per second squared. The negative sign is crucial. It indicates downward motion. Plugging these values into our quadratic model, we get the equation h of t equals minus 4.9 t squared plus 49t. We have successfully selected the appropriate function and created a model. But what about our assumptions? Let's be explicit. First, we assume gravity is constant at minus 4.9. In reality, it varies slightly with altitude, but for a toy rocket, this is a reasonable simplification. Second, and crucially, we are ignoring air resistance. Air resistance would slow the rocket down much more quickly. Third, we're assuming the rocket travels in a perfect straight line, we're ignoring horizontal motion and wind, and finally, the domain for this model is restricted. Since we can't have negative time, t must be greater than or equal to 0. As you can see, our simple quadratic equation is the result of many deliberate simplifications. This illustrates why understanding assumptions is paramount to interpreting any model. Let's work through one more example that doesn't involve the physical sciences, to broaden our perspective. Imagine a town with a population that is growing. You are given data for several consecutive years. Let's say in year 0, the population is 100. In year 1, it's 115. In year 2, it's 130. And in year 3, it's 145. Our task is to identify the best function to model this data and list its assumptions. Let's first analyze the rates of change. We'll build a differences table. The difference between year 1 and year 0 is 15. The difference between year 2 and year 1 is also 15. And so is the difference between year 3 and year 2. The first differences are constant and non-zero. According to our selection guide, a constant rate of change indicates a linear model. A linear function is of the form y equals mx plus b. The slope m is our constant rate of change, which we found to be 15 people per year. The y-intercept, b, is the starting value when x is 0, which is our initial population of 100. So our model is p of t equals 15t plus 100. What are the assumptions here? Our primary assumption is that the population growth rate remains constant at 15 people per year indefinitely. We are extrapolating the existing pattern into the future, assuming no factors like economic changes, natural disasters, or resource limitations will affect this growth rate. We are also assuming that time is our only significant variable. This population model is simple and useful for short-term prediction, but its long-term reliability is questionable precisely because of these strong assumptions. This demonstrates the critical importance of understanding a model's limits. Let's quickly review the key takeaways from this video. First, when selecting a function to model a scenario, you are essentially asking, how is the data changing? If the rate of change is constant, the model is linear. If the rate of change itself is changing in a linear way, or if the data is symmetric with one maximum or minimum, the model is quadratic. For more complex behaviors with multiple turning points, you need a higher degree polynomial. And for data that follows different rules in different intervals, you should use a piecewise function. Remember the powerful tools at your disposal: physical context, graphical features, and the algebraic test of the differences table. Second, it is crucial to understand and articulate the assumptions and restrictions of any model you create. No model is perfect. They are all simplifications of a complex world. They are built on assumptions about constants and relationships. You must define realistic domain and range restrictions based on the context of the problem, and be wary of extrapolating data too far beyond what you've observed. You are now equipped to approach modeling problems by thinking critically about the data, choosing the right mathematical tools, and most importantly, understanding the inherent limitations of those tools. This is a fundamental skill in all of science and engineering. Thank you for watching.